Namaste and welcome back to JEE Mathematics with Typical Monk. This is class 36. Probability. Probability is the art of measuring uncertainty, of putting a number between 0 and 1 on how likely something is to happen. It begins with the sample space, the set of all outcomes, and an event, a subset we care about. The classical probability is simply favorable outcomes over total outcomes. From there, flow the great rules, the complement, the addition theorem for A or B, the multiplication rule for A and B, and conditional probability, which asks how one event shifts the odds of another. Crown it with the Bayes theorem, which runs the reasoning backwards, from effect to cause, and you have one of the most powerful and most tested chapters in all of mathematics. Today, events, the addition and multiplication rules, conditional probability, and Bayes. One idea at a time. Here is what you will master today. First, the sample space and events. Second, the axioms and basic rules. Third, the addition theorem. Fourth, conditional probability. And fifth, Bayes theorem, one idea at a time. Let us set the foundation. Probability, a measure of how likely an event is between 0 and 1. The classical definition: favorable outcomes over total outcomes. The sample space, the set of all possible outcomes. Master line: probability turns uncertainty into arithmetic. Now look at the picture: events in a sample space. The sample space says the set of all outcomes. An event is a subset of it. The union, a union B, either A or B or both occurs. The intersection, A intersection B, both A and B occur together. The addition theorem, subtract the overlap so it is not counted twice. Now, the basic rules. The range. Every probability lies between 0 and 1. Certain and impossible. P of C equals 1 and P of the empty set equals 0. The complement. P of not A equals 1 minus P of A. The addition theorem. P of a union B equals P of A plus P of B minus P of a intersection B. Now, independence and conditioning. Mutually exclusive. Both cannot happen. P of a intersection B is 0. Independent events. One does not affect the other. P of a intersection B equals P of a times P of B. Conditional probability. P of a given B equals P of a intersection B over P of B. The multiplication rule. P of a intersection B equals P of A times P of B given A. Independence makes the multiplication rule simple. Now look at the picture, a probability tree. The tree, each stage of an experiment, branches into its outcomes. Multiply along a branch. P of a intersection B equals P of A times P of B given A. Conditional probability. P of a given B equals P of a intersection B over P of B. Add across branches for the total probability of an event. Now Bayes theorem. The setup, a cause we cannot see and an effect we can. Total probability. P of E equals the sum of P of cause times P of E given cause. Bayes theorem. It reverses the conditioning from effect back to cause. The formula: P of cause given E equals P of cause times P of E given cause over P of E. Bayes updates a prior belief with new evidence. Now a worked example. The experiment. Rolling a fair die. The sample space is 1 to 6. The event. Getting an even number. The favorable outcomes are 2, 4, and 6. The probability, 3 over 6, which is 1/2. Now match each rule to its formula. P of A plus P of B minus P of intersection B goes to the addition theorem. P of A times P of B goes to independent events. P of a intersection B over P of B goes to conditional probability. And 1 minus P of A goes to the complement. 4 pairs, each worth memorizing. Now, How many of these statements are correct? Statement 1. A probability lies between 0 and 1. Correct. Statement 2. For any two events, P of A union B equals P of A plus P of B. Wrong, only if they are mutually exclusive. Statement 3. P of not A equals 1 minus P of A. Correct. So the answer 2 are correct, statements 1 and 3. The trap is the missing overlap in statement 2. Now, the two mistakes that quietly cost marks. The truth: subtract P of A intersection B in the addition theorem unless the events are mutually exclusive. The trap: multiplying the probabilities of events that are not independent. The second truth: mutually exclusive is not the same as independent. The second trap: forgetting to divide by P of B in conditional probability. Now test yourself. Answer in your head before the reveal. That is how G-speed is built. Here we go. Question 1. The range of a probability between 0 and 1. Question 2. P of not A, 1 minus P of A. Question 3. The addition theorem, P of A plus P of B minus P of a intersection B. Question 4. For independent events, P of a intersection B, P of A times P of B. And question 5. Conditional probability, P of a given B, P of a intersection B over P of B. Let us gather it all in one breath. A probability lies between 0 and 1. P of not A equals 1 minus P of A and P of S equals 1. The addition theorem: subtract the overlap. Independent: multiply. Conditional: divide. Bayes reverses the conditioning. Next class: vectors. Reasoning under uncertainty. Probability is how mathematics reasons when it cannot be certain. Every event lives in a sample space and carries a number between 0 and 1. The complement fills in the rest. The addition theorem joins two events while subtracting their overlap. And the multiplication rule and conditional probability describe how one event bends the odds of another. Independence is a special, simple case where it is not. And Bayes' theorem completes the picture, letting us reason backwards. From an observed effect to the hidden cause that likely produced it, updating belief as evidence arrives. Master the ruse, draw the Venn diagram, sketch the tree, and probability becomes not a source of confusion, but a chapter of near certain marks. Next class: vectors. Sarah, David, Lisa, and John all began exactly where you are sitting now. One idea at a time, you will crack G. I will see you in the next class.